distance oracles.
Thanks for introducing. I'm Zhe. This is a joint work with my advisor, Michael Bingham. So first, let's see the definition. An approximate distance oracle is usually a pre-processing algorithm and a query algorithm. We're given a finite metric space. The pre-processing algorithm outputs a data structure, and whenever encounter a query QUV, the query algorithm outputs a new distance d prime, which is bounded by the old distance. Here, m is called multiplicative stretch and a is called additive stretch. And the objective is quite obvious. So we want a small data structure which has fast query time and a small stretch. So we should mention that if the data structure is large, then everything is trivial. So we can store the entire metric space within n square space. And the query time is 1, the stretch is 1. So we are focusing on reducing the size of the data structure. Okay. And although there are other distance oracles like hub labeling, Thorpe-Swift's work turns out to be the cornerstone of this area. They provide a distance oracle with 2k-1 multiplicative stretch and OK query time and kn to the 1 plus 1 over k space. And there are some improvements later which improve to O1 query time and to the 1 plus 1 over k space and some fractional stretches. And all these results either exactly include the Thorpe and Swift's data structure or partially include their data structure. So this shows their distance oracle is very important. And on the other side, stretch and reality provides a new distance oracle which has 2 multiplicative stretch and 1 additive stretch. And the query time is O1, and it takes n to the 5-third space. Okay, let's see a related problem, which is the spanners. Spanners has been talked a lot in the past few years. And it has similar settings and results to distance oracles. Like the objective is to find a small subgraph which preserves distances. The stretch factor is the same as distance oracle, and the stretch size trade-off is exactly the same as the Thorpe-Swift bound. And there is a line of work on approximating best spanners for each instance, like n to the 1 approximation algorithm for 3 and 4 spanners. So this turns out to be a natural question. Can we find the best approximate distance oracle for an instance, like what we have done in the spanners? Namely, given a metric space and a stretch bound, can we minimize the size of the data structure? So this turns out to be a hard question. It's hard in 2 ways. First, there is no certain definition of a data structure. So we are lack of tools on dealing with it. So the only thing we can imagine is like informational complexity discussion, but it does not work for a particular instance. And the other thing is that the best data structure is always O1. Actually, we can store the entire metric space in the query algorithm, so the data structure does not need to store anywhere. So what else can we do? One answer is fix the preprocessing and the query algorithm. We found that modern distance oracle have a similar property, which is the preprocessing algorithm randomly stores some distances which have a specific structure. And the query algorithm works as long as the stored distances satisfy some required structures. So, for example, the stretch 3 Thorpe-Swift distance oracle, they pick a vertex set randomly from V with probability 1 over square root of n for each vertex, and then store distance like this. The query algorithm works with these stored distances. There is a easy fact but haven't been mentioned anywhere before, which is any choice of A works for this query algorithm. So, and the only difference is on the size of the data structure. So why not just optimize the choice of A and reduce the size of data structure? So in other words, optimize the randomness used by the preprocessing algorithm. So now here we have a well-defined problem, which is optimization problem for a distance oracle. Given the preprocessing and the query algorithm, as well as the metric space and the stretch bound, we are aiming to output the random string used by the preprocessing algorithm. And in order to minimize the size of the data structure. Actually, this definition, we think this definition is one of our major contributions in this paper. Okay. So let's have a brief review of our results. For the throughput optimization problem on stretch 3 case, we give a matching upper and lower bound of log n. The upper bound is from reduction to classic facility location problem, and the lower bound is a reduction from a hard label cover instance, which is derived from parallel repetition theorem. So actually, the upper bound can also be given by LP relaxation and randomized rounding. So we think if we can, we try to extend it to a higher level case, which is stretch 2k-1. But we then find that there is a large integrity gap for the natural LP, so we can't do that. The instance is very simple, but the analysis is quite involved. And for the probability optimization problem, we also have a matching upper and lower bound of log n. The upper bound uses LP and LP relaxation and randomized rounding, and the lower bound is from reduction from set cover. Okay, we can also do some extensions. So sometimes there are some outliers in the data that makes the data structure blows up. So we can assume the data structure may ignore some stretch bound on some of the distances. So we have another definition of optimization problems for distance oracle with outliers, and we may ignore the outlier set F. So, and there are some results. Actually, the natural LP can't work in this case, so we move on to the SDP, and it works better. Okay. So now let us make a conclusion. In this paper, we introduced the definition of approximating approximate distance oracles and provide some results on throughput distance oracle, probability distance oracle, and distance oracles with outliers. There are still some open problems, which is like how to optimize it, higher level throughput distance oracles. Can we have better LP or better SDP? And another question is, can we optimize other distance oracles, like improved versions of throughput distance oracle? And a more general question is that, can we do optimization of other approximate data structures? Actually, our definition can be used on those data structures, like distance labels or compact routing scheme. And thanks, that's all about our paper.
Any questions?